it's very clear what's happening, okay, with the periodic. As I told you, in the first part till the break, okay, we keep on going. Then after the break, probably we do the parametric methods. And then at the end of the day, I got some files, okay, by one of you, by him. It's what? Vibration?
Yeah.
Okay. And so we make a spectral analysis on his file, or whatever is the file. It's a 3-axial, right?
3-axial.
Okay. 3-axial means 3-dimension, right? Okay. And which is similar to what is you have inside here. This is 3-axial as well. But is it better calibrated yours, right? You're good. Okay, so this is a joke. This is like a joke, but those measurements probably it's made with equipments that are more expensive. Okay. So anyway, we take a look at. I don't know what it's about, but we'll take a look at together. Now, my goal is that spectral analysis. Okay, as I told you, so it's close to be an art. And so it's important for me that it's very clear what is happening. So let me go on. So I decided to make a very small proof, okay, which is illustrated by this formula that probably is sliding away. Okay. So now let's go to the point. So this is what we discussed Saturday, okay, for those that were there. So the spectral analysis is estimating the power of spectral density by having a finite, limited set of data. Now, so what the non-parametric method is doing, which is a periodogram. The non-parametric method is the formula. Okay, it's very simple. It's taking. Let me see. Yeah. Okay, this is the definition. Huh? So I take the set of data, the samples, and then I calculate a discrete Fourier transform. I make the square for the discrete Fourier transform. I divide by the number of samples. This is an estimator of the power spectral density. It's non-parametric because I'm not assuming any a priori model on the power spectral density. How is the shaped and what is the behavior. Now this estimator is biased and is proved by this formula, and for those that were not here, they can see on the movie, right, on the YouTube. Okay, and the variance as well. Now the variance is very big. Now we will see what does it mean that the variance is the square of the value, but I want that we capture a little bit about the meaning for these concepts. Now it's a square except on 0 and Nyquist frequency, whenever the Nyquist is present, where the variance is 2 times. Okay, so this estimator is biased, which means it's a disaster, and it has a very big variance, which is even worse. So this estimator apparently is useless and not worth of any, any effort to use. But it's so common, so popular, and it's the most useful estimator for power spectral density that after facing that is biased and with a big variance, we need to cope with that. We need to find a way to reduce the variance and trade for the bias. Now, this was a discussion. Now, essentially, what the spectral analysis does is the following. So I have a bank of filters, many filters, okay? And every filter which is here, so I have a filter 1, filter 2, filter k minus 1, k minus 2, k minus 1, and then I have a filter k at the frequency omega k, where omega k is 2 pi divided by n multiplied by k. Okay, so this is the specific frequency here. Okay, So, you know, that means that the frequency are bin. It's a set of bin. And the bin are equally spaced 2 pi divided by n. So I have a set of frequency uniformly spaced in the spectrum, normalized spectrum between 0 and 2 pi, or minus pi and pi. Okay? Now, so what's happened on that? Now, it happens the following, that every filter captures the power which is included in the filter itself. So essentially, this filter captures, so it makes a filtering and capture all the power which is included inside in this area. So now the power spectral density estimate inside in this interval, it is the power spectral density multiplied by the bandwidth. Okay, this is, you know, what is the power in this band. But you know, since the power spectral density is the power per any bin, so you know, S omega, which is the power divide in every filter, divide by 2 pi, so 1 over n is the power in this bin. Now, by the way, for those of you that are coming from the analog electronics or analog life or analog whatever, this is the principle of spectrum analyzer. That's a measurement device. Okay, so the spectrum analyzer is measuring the power spectral density using this principle. But you know, rather than having a bank of filter, there is one filter which is sweeping in time. Okay, it's sweeping. So it measures the power within this pass band filter, and the filter is moving in time. Okay, so essentially the periodogram is coming from that idea, the idea that the spectrum analyzer is measuring power within a certain band. So given that, let's take this concept and, you know, pull it. So now what I want to prove today now, you know, is the motivation, the intrinsic motivation why the variance of the periodogram is too big. Now, which is what I'm proving is what is written here. Here. Okay? So I'm taking these sentence, let me say, and I'm proving that. Okay? Which you surely didn't do that. So, you know, I want that you are quite aware about what does it mean. So let me find some page for some room here. It's copied here, but you know, I want that you understand every step. So let me do like the undergraduate level. So let me say. So you know, what does it mean, the periodogram? The periodogram, as you have a power spectral density here. This is omega. And so, you know, the periodogram is measuring the power in every bin. Okay? So, let me call these frequencies omega k, and let me call this value, which is the power spectral density, so this is S omega. Okay? Let me call this one as S omega k. Okay? This one is the power spectral density value at omega k equal to pi divided by n multiplied by k. Okay? That's, you know, that's what we have. Now, what is the periodogram? The periodogram, okay, is defined as S at omega k. And you know, if I follow the definition, it is equal to the absolute value of the discrete Fourier transform computed in k squared divided by n. Now, what does it mean? It means that, you know, I have a real part at the sample k squared plus x imaginary part squared at the sample k divided by n. Okay, this is what the periodogram does. So, you know, looking at the property of each individual real and imaginary part, we know that x real part k is behaving as a Gaussian, which has a zero mean and the variance, which is n divided by 2, and the power spectral density omega k. Okay. For proving of that, see the book. There is a proof of that, which is just 5 lines. I don't want to use this time for these 5 lines. Now and then similarly, the imaginary part has the same distribution, but x real k and x imaginary k, they are orthogonal. Now, why they are orthogonal intuitively? They are orthogonal because one is taking the in phase and the other is taking the quadrature signal. One is taking the projection of the signal onto the cosine basis, and the other takes the projection of the signal onto the sine basis. Okay? So they are mutually orthogonal. Perfect. Then, that means that if I just write, so just to simplify the notation, okay? So I write to simplify that pk is the power spectral density in omega k. P hat k is the estimate, okay? And then I write the estimate in this way. So x real squared plus x imaginary squared divided by n. So what I'm doing is just, this is to simplify the notation. Okay? So let me, let's use this pair of definition just to simplify the notation. Okay? Just to have a very easy notation. Now, according to the properties above, then that means that, we can calculate the expectation of a p hat k. And so the expectation of p hat k is equal to the expectation of x real square plus the expectation of x imaginary square divided by n. And now, if I just take it from the definition above, so so this one is n divided by 2 pk plus n divided by 2 pk, everything divided by n. Okay, this makes a pk. So we say that the estimator is unbiased. We know already, but let's look at with a different, slightly different way. So what I want to prove now is I take this definition and then I calculate the variance. So now I need to change the page. So I see you are copying. So you have recorded, you have the pages. So I can swap the page easily. Now I take the variance property. So let's see. So what I need to calculate is the variance of a p hat k, okay, which coincide with the variance of periodogram. Okay, so what is the variance? The variance is equal to the expectation of, now it is p hat k minus pk squared, okay? So this one is p expectation of p hat k squared minus pk squared. That's because it's unbiased, okay? So, now let's go on that. So what is the expectation of a p hat k squared? Now let's look at that. Now this is the expectation of, what is a p hat k? So it is x real square plus x imaginary square divided by n. Now, so according to the definition, it's to the square. Okay? because it is the definition of parallelogram to the square. Now, so this one is equal to expectation of x r to the 4th power divided by n squared plus expectation of x imaginary part to the 4th power divided by n squared plus 2 times divided by n squared expectation of, let me put on a new line, 2 times n squared expectation of x real squared expectation of x imaginary squared. Now, what is x r to the 4th power? So x, you know, if I go there, x is Gaussian, okay? So we know that, you know, if, I mean, this is the property I'm using, I put in a different color. If x is Gaussian with a certain variance, sigma square, okay, then, you know, expectation of x squared is equal to sigma squared. The expectation of x 4th power is equal to 3 times s sigma to the 4th. Okay? This is the property of Gaussians. And this property is exploited when defining some statistical indicator, which is used for understanding if a distribution is skewed or not. And for instance, if a distribution, so if a random variable which has a certain distribution, it has a 4th moment, which is larger than 3 times sigma 4th, then we say that it's super Gaussian. If it is lower than that, we say that it's sub-Gaussian. Okay? So there is also all a liturgy to define these non-Gaussian distributions. That's because super Gaussian and sub-Gaussians, you know, they have different behaviors. Now, we did not stress too much this aspect. For those of you that in the life, you know, or perhaps in the thesis are working on with the non-Gaussian distributions, that probably would be the case for if you are doing something in an advanced way, then you know probably need to deal with these distributions and with these concepts. Anyway, so let's continue on proving. So here we have a 4th power. So the 4th power is the variance to the square, okay? And the variance was the power itself. So let's apply the rule. So this is equal, according to that, this is equal, so it is 1 over n squared, because n squared goes to all over, okay? Then, you know, I have the expectation of x r to the 4th power. Now, what is the variance? The variance is n divided by 2, and then the power spectral density, which is p. So it is n divided by 2 multiplied by pk. So this one is 3 times n divided by 2 multiplied by pk. This is the variance. Okay, so it's the variance to the square. Plus 3 times n divided by 2 multiplied to pk, everything to the power 2. Plus, it is 2 times, then here I have the variance of one and the variance of the other. Okay, so I have n divided by 2 times pk times n divided by 2 multiplied by pk. So I computed piece by piece. Okay, so you know when I group, so here I have n square, n is n square, I have n square here, so they simplify. Then I have a pk square, pk is a pk square, They simplify. They can be grouped. So I have, I have 3 times to the power of 2, so it's 4, plus 3 times 4, plus 2 4, so it is 1 half. Multiplied by pk squared. So this guy is 3 4, 3 4 is 3 half, plus 1 half is 3 4, 3 4. Yeah, is 2 times pk squared. Okay. Now, what is the variance? So the variance, bringing back the last equation, is the variance of pk hat is equal to pk squared minus pk, which is pk squared. Okay. Now, so the variance is the power spectral density to the square. So now let's go backtrack to understand by this one what is the main reason to have such a big variance. Now the reason to have such a big variance is making a backtrack, so it's here. So here I have just 2 random variables. So I'm making the average of 2 random variables, which is the real and imaginary part. So if I have more random variables, then making the average of more random variables, the variance is reducing. So exploiting the property that the variance of the sum of random variables, the variance of the mean of, which is the sum divided by the number of random variables, scales down with the number 1 over the number of random variables, then I can find the rule to minimize the variance. So, the rule is by exploiting the following property. So, now, how to reduce the variance. Okay, now, recalling this property. Recalling that, now if I calculate, x1 plus x2 plus blah 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 plus xn. So if I calculate the mean of a set of random variables, such that these random variables, so xi, is independent and identically distributed. So which means, these are independent, okay? They are statistically independent and are also identically distributed. Now, if I calculate the expectation of this sum, let me call as a mean. So the expectation of the mean is equal to the expectation of each individual variable. And since they are identically distributed, it's mu x. Okay? So, what is the variance then? The variance of x naught. Now, since they are statistically independent, this is equal to 1 over m squared times the variance of the sum. So it's 1 plus x2 plus blah blah blah. But since these quantities are statistically independent, this is equal to m times the variance of each individual variable divided by m squared. So, which means that the variance is 1 over m times the variance of the individual xi, which, might be sigma squared x. So, that means that in order to reduce the variance, we need to average. That's the point. So the periodogram averages only 2 variables because it's a real and imaginary part. But what we need to do, we need to average more. Okay? So we need to take all the data and find a way to average the data. or actually average the periodogram, not average the data. So essentially, what is coming out is this one. So if I can get the periodogram, or different periodogram, I need, so how to reduce the bias? I need to average some periodograms. That's the solution. So how? That means that I need to take the data and divide it in pieces. And out of each piece, I can calculate the periodogram. And then I can average the periodogram. The solution is very stupid, but I mean, it's, that's the way, that's a basic idea. So, going to the point, okay, is it clear so far? Now, let me add one comment. In this, for here, I made the assumption, so making my computation, I made the assumption that the periodogram is unbiased at a certain point. And then, before you ask and you raise the issue, I can tell you that, I made an assumption here that the power spectral density is one of those that do not bias the periodogram. And there are some power spectral density that do not bias the periodogram. In all the other cases, there might be some bias, but my goal is to look at the variance, not the bias. And so according to that, all the reasoning holds, provided that, let me write here, provided that here I choose choosing the power spectral density where bias is 0 or small. Okay? So all the reason I'm doing here is for all the power spectral density where the bias is 0 or small. If it is not 0, if it is not small enough, then that means that there is a bias to take into account. But the rule for the bias still holds. Okay? So now given that, let's see how to reduce the variance. Now the way to reduce the variance is, let me say, quite intuitively in the light of what we discussed so far. So what I need to do is this. So I need to take all the data, segment means a piece, take a piece of a subset of data, compute the periodogram of each subset, and average. In other words, that means that assume that I have a very big data set, such as the data set is n times n. N is the number of segments that you use to segment the overall data. So then I decide that I take a set of subset n in such a way that there is in total m subsets, capital M. Okay? So I have these subset which I indicated as x1. I have a second subset that I indicated as x2. And blah 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 until I have the m capital M subset that I indicated as x capital M. I calculate a periodogram for each of the subsets following the rule that we already established. And then, how do I make it? The periodogram, so the average periodogram is by summing all that divided by n. That's it. And so this new one is the periodogram, so the estimated periodogram using averaging of m subset, okay, of calculated in omega k. So, if you remake all the analysis, it comes out that in this case, okay, the variance as expected reduced by 1 over n. Clear? You need to go back. Go back to YouTube. No breathing. Perfect. Okay, so the variance, the simple way, which is very simple, the variance is reduced by trading actually, by trading the bias with the variance. Why is it that? Because we know that, this n, capital N times capital N is a total data set. So assume that, now we discuss that. So assume that now I have my complete data set, blah, 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 which is the same that we do after, okay? I have a data set, which is whatever samples I have, okay? So now I have this complete data set. So is, I don't know, is 10,000 samples, okay? This is total data, which is music, which is whatever you prefer. Then what I can do is this. I can either decide that the total data set is 10,000. So that means that my subset is 1. So I take all the data and make one periodogram. Okay? Now, so if I choose, let me say, if I choose n equal 1 and n equal 10,000, what's happened? It happens that one window. So we remember that the bias of the periodogram is going to 0 for n going to infinity. So in this case, the bias is low and the variance is high. Is the highest, okay? Is the worst case. Now, in the other case, I don't know, I can choose like n equal 100. And that means that n equal 100. Okay? So what's happened here? That the bias is high and the variance is low. So if the bias is high, basically here I lose resolution. I lose selectivity. Okay, where the selectivity is the capability to follow a sharp transition in a power spectral density. But the variance is low. So essentially, given the total data set, so given the data, I need to decide, I assign to the data the total, so the assignment, which is n times n. So what I can do this way. I can trade between bias and variance. Okay? And so, it's like being in the middle. So, you need, it's like you're there and you need to decide if you want more bias or more variance. Okay? I told you, I don't give you the solution to your problem. I give you the tool. I tell you what is the limit of the tool. I tell you how to trade one with respect to another. How, in a sense, what is impairing, what is affecting this and that. I don't tell you that the golden rule is to use blah blah, because it depends on the problem. So if your problem, for instance, has some important aspect on the edges, because you want to find some sinusoid, which is very, very close to a transition, as what we saw Saturday, then in that case, you are better to tolerate high variance and make n very big. And on the other hand, if your goal is to estimate the power spectral density with high accuracy, and the fluctuation of the power spectral density matters, then you're better to choose a low variance, because in that case, the fluctuations are dependent on the number of blocks that you are using. Okay? So, this is a trade-off. So you can either choose one block or you can choose sub-blocks. Okay? Now, so another approach. The other approach, which is called the Welch method. The other approach is this one. We saw Saturday that, you know, in some cases, I can avoid the side lobe, which is a spectral leakage, by choosing the window. The window has the property that by window you have a side lobe, and the side lobe are, you know, are going down faster rather than segmenting, which is taking a rectangular window. When you segment, you take the data tuck, okay, which means you cut the data. Okay, in MATLAB it's a stupid operation because you simply assign the piece of data to a subset. So, okay, so when you segment the data, then, you know, you are segmenting and cutting, but implicitly you are windowing by a rectangular window. So if you window by a rectangular window, what's happened is that you have a certain set of side lobes, and the side lobes are depending on the cutting by the rectangular window. A rectangular window has a side lobe that, you know, is decreasing as a sink, and since we are considering the autocorrelation is decreasing as a sink square. Okay, but, you know, I mean, decreasing by sink square means that the side lobe, okay, if I take a rectangular window in data, then, you know, this is the on data, then on the power spectral density, the bias is given by a sink square, okay? Because it's the power. Now, so that means that, you know, the side lobe here, this side lobe is too high, it's too big, okay? So this side lobe introduces the spectral leakage. Let me say, this is, with the rectangular one, is the largest spectral leakage. So what we can do alternatively, rather than window in this way, you know, we can window with the triangular one. The triangle is with the same aperture, so it's N. Now, if I window with the triangular, with the triangular one, okay, like here, so that means that if here I have a sink square, here I have a sink to the 4th power. That means that the side lobes are decreasing very quickly. Okay? What is the drawback? The drawback is the following. A triangle is obtained by convolving to a rectangle. Okay? And the rectangle is n half. So that means that what I expect, okay, it's not in scale. I expect that the aperture here, okay, or the first zero, say, the first zero here, okay, here is 2 pi divided by n. Here is 2 times 2 pi divided by n. Okay, or if you like in that way, it is 2 pi divided by n half. And this is due to the half of the window. Okay, so the side lobes are decreasing quicker. So that means that is a lower spectral leakage. Once again, which one do I have to choose? It's the same. You know, if you want to preserve the transition, okay, then you choose the rectangular one, because if you use the rectangular one, then, you know, the transition, so the selectivity is the sharpest that you can tolerate. But on the other hand, you have a spectral leakage. If you can tolerate the transition, but the spectral leakage is annoying part, then you can choose to cut the window by a triangular shape. So it depends on the case. Once more, it depends on different case. Now, so in the book you have a specific example, you have a code for that, by the way. So you have one specific example where I copied here, and we commented last time, but you know, I just for the sake of the others, okay? So this is the behavior here is the true power spectral density with this dashed line, okay? So that is the power. That is a true power spectral density. Now, if I calculate the power spectral density with the periodogram, cutting abruptly, which means without smoothing the periodogram before computing the periodogram itself, then I get this power spectral density, this behavior of the power spectral density. So this is with the rectangular windows. If on the other hand I window with the triangular one, so what's happened is that I can get this estimate of the power spectral density. Now you see that from the estimate, the transition is perhaps slower, it's decreasing by a factor of 2. You don't even see that, okay? But I mean the side lobe which are creating the spectral leakage are negligible, at least for the scale that I indicated here. So for the scale here, I don't have a spectral leakage. Actually, the spectral leakage are here, okay? But far below. So I mean, in this sense, what happens is that I realize that I can estimate that there was a small, tiny sinusoid hidden into the other signal. Now, if this is not, this is a signal that has a limited bandwidth, is, I don't know, whatever, is the noise, is the signal generated from one source. And this is the second sinusoid, which is generated by the engine of a submarine. And it's important to detect the engine of a submarine, because from the engine, you understand that that is your friend or not. Okay, then according to that, it's important that you design the spectral estimation in order to get the frequency that you want to estimate. You see that? Because you don't see the sinusoid in this case. Now you understand in this plot some meaning there. So that in this plot I have m equal 20. Now you understand why. Actually Saturday, nobody raised the issue because it probably was a Saturday. But so nobody raised the issue that the variance is not that big as one expected. And the reason is because I choose m equal 20. So this is the result of averaging 20 simple periodograms. Okay? So it's the Bartlett method with the 20 periodograms. Okay? And and I can choose another window, such as handing or so on. So I can choose. So I have my database. So if you type on MATLAB windowing, so it comes out a lot of different windows. Which one is better? Try. Get the feeling on that. Some windows are better in some cases, other windows are better in other cases. Okay? So it makes no sense that I illustrate all the possible windows that exist, because you can do by yourself. You go by MATLAB, or you can go your professional code. MATLAB is also professional, is getting professional now, but you use your own professional code, and then you find a window which is more suitable for you. Okay? Now I told you spectral analysis is an art, so you need to find a way to put together. And once you become an expert on spectral analysis, you have a job. Because there are many applications where you need the spectral analysis. The spectral analysis that we are discussing and the spectral analysis that are for line spectra that we don't discuss. Okay, but you can find in the book. So now let's continue on that. Making the window. When I make the window, there is something that you might improve. So this is something it's very easy. So when I make a window, look at that. So I have my data and I window with this. So the window is made in such a way that here is 1, here is 0. So the data in the center counts more than the data on the side. So, I mean, if I make a window on my data and the window is chosen as a triangle, so what I expect is that the data in the center, they count, but at the end, the data on the side are smoothed down. So I'm losing energy. Because, I mean, by tapering the data on the left or right, positive and negative value of the time, that means you are losing energy. So how to compensate for this losing energy? You need to do an overlapping of the window. So essentially, when you window, the second window is not just one after the other. So rather than the window being here, one after the other, where in this case you lose the energy, you see? Because I mean the samples here in the center, they are never used. Actually 0, or it's very small. So I make a second set of windows, okay, which is overlapping with the first one. And so the collection of all the windows, which contains an overlapping factor. What is the overlapping factor? The overlapping factor is how much they overlap with respect to the total window size. So if the overlapping factor is 50%, which means the K factor, the overlapping part is half of the total aperture, then what I can have that all the data are exploited. Okay? Now, the overlapping factor can be optimized with respect to the time of window. Again, that's something that you can test by yourself. It depends on the case. So I mean, I don't spend too much time on saying cases by cases, because I mean you can find a different data set to manipulate, to process, to estimate the power spectral density, and then the rules are perhaps not exactly applied. So this method is also a way to reduce the variance as well. Okay, so I mean in this way I reduce the variance, and I mean the variance here does not exactly reduce to the, so it reduces to the total number of windows. So if I make an M window, so it reduces approximately to the total number of windows. In the book there are some coefficients that I calculate to see exactly how much the variance reduces. But so that's now. These are two examples, but there are many. So when we will open MATLAB, you will see several other options, several other possibilities. Okay, and in MATLAB, what you need to design, you design how much is this interval. So what is the lag between the first window and the second window, which is similar to applying for the overlap. Okay. Good. So, Blackman 2K. So there is another way that you can also use. We don't discuss that, but there is another way to to reduce the variance of the periodogram, which is by filtering, by convolving the periodogram by a window. That's another option. Okay. Which is Blackman and 2K method, which is here. So, yeah, so, that's, I think I said all, I told you all I had to say about, the periodogram. And later we will see. So you remember all that, and we will see applied on the couple of examples. So one I generate synthetically, the other is the data that we got, and we manipulate those data. Now, let's move to another aspect. Now, the other aspect, before coming here, I saw the slide, and I prefer to look at the slide in another way. I look at the bottom of the slide. Now, so far, we have on one side the covariance matrix. And the covariance matrix is the matrix that we get, okay, by calculating the correlation property of a set of samples. On the other side, we have a power spectral density. So, you know, and you might say, but how can I reconcile the two? Now, intuitively, what I expect is that if, you know, if I have a stationary random process, in a stationary random process, what I expect that there should be a relationship between the power spectral density and the covariance of a set of data. Since it is stationary, this covariance computed on the block is the same that the covariance computed on the block where I shift by arbitrary number of samples because of the stationarity. So I have a block of data. Here I compute the covariance matrix, but you know, if I compute here, that's the same. So, you know, at a certain time, I told you that there is a close relationship between the eigenvector and eigenvalues of the covariance matrix with the Fourier transform basis and the power spectral density. Now this relationship is important because we are now moving into the parametric methods. The parametric methods means that we are assuming that the random process now is autoregressive, moving average, or Armand. Now, what is unclear is how can I write the Lagrange function? Because if I need to write a Lagrange function, so far we know how to write the Lagrange function when we know the probability density function. So if I give you the PDF, then you can write the Lagrange function, because you know from the PDF you can write the Lagrange. But what about you know, in power spectral density estimation? Now the link between two sides is given by these simple properties. And the property is this. If I calculate, I start from the bottom, okay? So the slides 1, 2, 3, 4 are just the proof of this theorem. I don't frame as a theorem because, you know, I'm against this approach. But, you know, I mean, I frame it as a property. So the property is the following. Assume that I have a stationary random process. And I calculated the eigenvector. So, having a stationary random process, I can calculate the covariance matrix. You know, since it is a stationary, this covariance matrix is duplet structure, which means that the CXX Ij, so the entry Ij of this covariance matrix is the autocorrelation of X. Okay? So it is Rx X I minus J. Okay? This is the property. So when I say duplet structure, means that, you know, it has this structure. So what about computing the eigenvector? So I can always compute the eigenvector. The matrix is positive definite or semi-definite. Then, you know, I can calculate the eigenvalues and eigenvector. So this is the definition of eigendecomposition, where Q are the eigenvector and lambda is the diagonal matrix containing all the eigenvalues. Okay. So what we have here is, you know, is this decomposition. So far is all we know. Okay. So this is just all known. Now, what is new? The new part is that, you know, let me say in general, there is no relationship between the eigenvector and Vk. What is Vk? Vk is the basis of the sinusoid in DFT. We write here. So dk is the k sinusoid. So it is aj 2 pi divided by n multiplied by k times 0. aj 2 pi divided by n multiplied by k 1. aj 2 pi divided by n multiplied by k times n minus 1. So in this n times 1 vector, okay, this is n times 1, you know, you have a sinusoid. So if I put the time axis in this direction, so this is the label 0, this is the sample 1, and this is the sample n, which is corresponding to that. Okay? So what I'm representing here is, in this vector vk, is a sinusoid, so if you like, that makes an integer k cycle in the n samples. Okay? Here represented k for 1, so you know, or more. Okay? So these are the samples. So I have a sinusoid, a complex actually. Okay? That makes k cycles in n samples. This is the vector vk. Okay? So there is no relationship, you know, between the eigenvector qk with this one. This is a sinusoid. Qk is the eigenvector. Okay? There are two words. So you didn't notice, but you know, so far we have been treating in the first part the covariances. In the second part, now we are treating the power spectral densities. Now, you know, is there a link? And now I'm telling you the link. So, if I make the covariance matrix very large, if this covariance matrix is very large, so if I use a very large set of samples, infinite, okay, large enough, we say, then what's happened is that, you know, what we get is that qk coincides with that, with vk. So asymptotically, the eigenvectors are complex sinusoids. And the eigenvalues, that's a very important property, coincide with power spectral density of x. Here it is the link. So that's the link between the two. So the link is that, you know, for a very large number of samples, large enough, whatever you want to say, okay? So the eigenvectors and the sinusoid coincide, which means if I look at the eigenvectors, they behave similarly to a sinusoid. Now, if the number of samples is limited, okay, so if the number of samples is limited, and I represent Q1, for instance, okay, then what I see is something that is behaving this way. If I look at Q2, then you know what I get something that is similar to a sinusoid. It's a smoother there. Okay? Now, if rather than taking this window, I take an infinite window, then you know they are perfect sinusoid. That's what happened. So this is for n going to infinite, or you know, very, very large. So for n very, very large, you know, it's similar taking the eigenvector or taking the basis vk. This is the basis of the Fourier, right? Of the discrete Fourier transform. is the basis of the discrete Fourier transform for periodic sequences. Right. Now, what is the proof? Now, after telling you the story, let me tell you what are the steps of the proof. I'm not showing the proof. Okay? I would say it's a very nice exercise to look at the proof. You can challenge yourself to see if you can follow the proof. Perhaps, in the slides it's too compact. If you go to the book, it's more extensive. Okay? Now, but the key point is this. If I calculate the covariance matrix for a periodic signal, okay, then what's happening is that the covariance matrix for periodic signals, then the good news is that the sinusoids are the basis for the covariance matrix of periodic signals. Now, if the period is getting very, very big, infinite, then I get the covariance matrix for a periodic signal, because an aperiodic signal is a signal or a random process that has a period going to infinity. So what is the trading between one and the other? Is that if I take a limited set of data, I have some hedge effect. So these are hedge effects. So it's not a perfect sinusoid. By the way, if you look at it in the center, the eigenvector is very, very similar to a sinusoid. What makes the eigenvector different from the sinusoid is on the edge, at the beginning and the end. So this is what you expect. So if you calculate the eigenvector of the covariance matrix, you will see, it's easy. You make plot of the eigenvectors, right? They are complex, so you make a plot if the matrix is related to a set of complex signals. If it is real, you can calculate the eigenvectors. Since MATLAB, is computing real and imaginary part, try yourself. If you have an imaginary part, the imaginary part is, is 10 to the minus 5 times smaller than the real part. This is due to the fact that MATLAB is computing using complex numbers, and then there is some numerical error in the computation. So, beside the numerical error, you can make a plot. So we have a covariance. Take the exercise, take the homework, calculate the correlation, build the covariance from that, calculate the eigenvectors, look at the shape of the eigenvectors, look at the shape from the beginning, and you will see that the behavior is very similar to the sinusoid. Okay? So in this way, if you make by yourself by MATLAB, okay, MATLAB is just a way, so it's something that's easy to do. Then you convince yourself about that. Then you are not surprised. And then, this writing, so this, what I'm writing here, freezes in your mind and doesn't go out anyway. Okay? Now, what is the major difference? The major difference is that if you take a MATLAB or any code usually order the eigenvectors according to the decreasing eigenvalues. Okay? Here, what we get is this. Since Vk is a sinusoid, we decide the ordering because we choose k. Now, so in order to reconcile that, if you calculate the eigenvector for a low-pass signal, low-pass random process, then perhaps the first eigenvector is the first sinusoid and the second and so on. If you have a high-pass process, high-pass which is dominating with the high frequency, then the first eigenvector, which is related to the largest eigenvalue, contains a very fast variation. Now, so this is the remark number 2. The remark number 2 says, in software programs, for numerical analysis, the eigenvectors of the covariance matrix are ordered for increasing or decreasing eigenvalues. Okay, so that means, I mean, the eigenvectors are ordered for, in MATLAB, I think, is in decreasing order, okay? But you know, it's, you can see. In decreasing order of the eigenvalues. Here, okay, the power spectral analysis is ordered with respect to the increasing frequency, as the eigenvectors are predefined as a basis of the Fourier transform, because this is VK. So you decide the basis. And so you get to the power spectral density that it happens for that particular case. Now, from this rule, you understand, recall, that for LNS algorithm, okay, the convergence rate depends on lambda max over lambda min. You remember? And we said this is equal approximately as the power spectral density max to the power spectral density min. Okay? At that time, I had no tool to show you where it's coming. Okay, that's where it's coming. Okay, just just to recall the property. Okay, now, so I'm not showing the proof, but before. Okay, we make the break here. So since we are moving in this in parametric spectral analysis, okay. So just to break the day in a way that is place a discontinuity where there is a discontinuity. Okay. Let's keep it short because I want to make that exercise. Okay. Keep it short means really 5 minutes. I look at it like.